Our next unit is going to be about triangles. So this video has a lot of definitions and a lot of theorems, so make sure if you need to, you pause and write down everything and then continue at your own pace. So first we're going to talk about classifying triangles. So let's look at some basics. First of all, if we have a triangle, it's a three-sided polynomial. We might label it A, B, C. So we would call this triangle ABC. Alright, there's different ways of naming your angles. You might say angle A, angle B, and angle C. Or you might say angle BAC. As long as the angle you're referring to is directly in the middle. So then angle B could be angle ABC, and angle C could be angle ACB. And it doesn't matter which order, as long as you could say angle ABC or angle CBA, as long as you're referring to angle B. And our sides we might label with a lowercase letter across from the angle. So if we have a capital A over here, our lowercase a would be directly across. So we have lowercase a, lowercase b, and lowercase c. So our sides, we can simply label them as ABC. Or instead of saying side A, we can say side BC. Instead of side B, we can say side AC. And instead of side C, we can say side AB. We can also denote congruent sides by a dash. So if all three of these sides of this triangle were congruent, we could put a dash in each one. And that would just tell us that they were all the same length. Sometimes you might have two congruent sides. So two congruent sides would both have a dash, and then maybe your third side would have nothing or two dashes to denote that it's a different length than the other two. And sometimes you might have three different sides. So you might have 1, 2, 3. And similarly, we do the same thing with angles except with curves. So we kind of have a little curve on each angle, which would denote that all three angles were the same. And just like with the sides, if two angles were the same but one was different, you might have a double line curve. And then if they were all three different, you might have one with 3. Alright, what's important to also remember is that the triangles, all the angles add up to 180 degrees. It's actually called our triangle angle sum theorem, but we'll get to that in a little bit. It's just important to realize or remember that they add up to 180 degrees. Okay, let's look at some more stuff. We have our angles. Supplementary angles add up to 180 degrees. Complementary angles add up to 90. So if we had a straight line, that's 180 degrees. So if we cut that line, we have two angles. We have angle A, angle B. If they're supplementary, that means you're going to add to 180. So both of these angles together would make 180. Complementary, we add to 90 degrees. So we have that right angle. And so if we cut that somewhere and had angles C and D, angle C plus D would equal 90 degrees. And we have three different types of angles. We have acute, right, and obtuse. Acute angles are less than 90 degrees. So that would be an acute angle. A right angle equals 90 degrees. That's where we have our little square in the angle to denote a right angle. And an obtuse angle is greater than 90 degrees. So it's going to be kind of like that fat angle. Alright, so if we look at classifying triangles, we have two ways. We can classify them by sides and we can classify them by angles. So if we classify them by sides, we have three different kinds. We have an equilateral triangle where three sides are congruent. This is a terrible equilateral triangle. We can denote that with our dashes, that three sides are congruent. We've got an isosceles triangle where at least two sides are congruent. So we can denote that with 2 dashes. And then we have a scalene triangle where we have no sides congruent. This is where we could denote our 1, 2, and 3. Okay. We can also classify triangles by angles. We have acute, obtuse, right, and equiangular. An acute triangle has 3 acute angles. So that means all 3 of the angles in our triangle are less than 90 degrees. Right? All 3 of those angles. An obtuse angle, or an obtuse triangle, has 1 obtuse angle. So that means you kind of have 1 fat angle and 2 acute angles. And then we have a right triangle, which has that 1 right angle and 2 acute angles. And then we have an equiangular triangle. And that means all 3 of our angles are congruent. So this we could denote by our curves. All 3 angles are congruent. So we're going to be looking at a lot of theorems in this unit. So let's talk about what a theorem is. A theorem is just a statement that can be proven true by undefined terms, definitions, and postulates. So it's just something that mathematicians have proved, and we can use it to further our understanding and make new proofs. A corollary is a theorem with a proof that follows as a direct result of another theorem. So we'll look at some of those in this unit. Let's get back to that triangle angle sum theorem. That's the one that says the sum of the angles in a triangle is 180 degrees. From that, we know that acute angles of a right triangle are complementary, and that there can be at most 1 right or obtuse angle, and the other 2 angles are acute. So in our acute angles of a right triangle, terrible right triangle. So if we kind of look at this, here's our right angle, so we know that that's 90 degrees. So if we know all 3 of those angles have to add to 180, if we subtract that 90 degree right angle, we're left with 90 degrees. So that means that our other 2 angles have to equal 90 degrees, which makes them complementary. If we look at the obtuse triangle and right triangle, in a similar way, we know that it has to add to 180 degrees. So if we subtract our 90 from 180, we know that we get 90. Equals 90. So that tells us that the other 2 angles have to be less than 90 in order for them to add up to 90. And then similarly for our obtuse. Our obtuse is anything over 90. So that means if we take 180 and subtract anything greater than 90, we're going to get something less than 90, which means those other angles have to be less than 90. So they have to be acute. Alright, we have a new theorem, a triangle inequality theorem. This just says that the sum of the lengths of any 2 sides of a triangle must be greater than the length of the third side. So for example, if we look at a triangle that has sides of 8, 15, and 17. 8, 15, and 17. We can apply this theorem to see if it works as a triangle. So if we say 8 plus 17 equals 25. 25. And we look at 25 compared to our other side of 15. And 25 is greater than 15. Now that one works. Then we can look at 8 plus 15, which equals 23. And 23 is greater than 17. So that one works. And then we look at 15 plus 17, which is 32. And 32 is greater than 8. So we know that this is a triangle. Another example, we could look at triangle with sides 6, 8, and 14. So 6 plus 14. So that gives us 20, and 20 is greater than 8. 14 plus 8, which gives us 22, and 22 is greater than 6. And then 8 plus 6 equals 14. Now 14 is not greater than 14, it is equal to 14. So it doesn't fit our theorem, so therefore this is not a triangle. So that one is not a triangle. So pretty much what we've looked at so far. Let's change the color. Okay, so this triangle inequality theorem just tells us if we have a triangle with sides A, B, and C, that the sum of A plus B has to be greater than C. And then B plus C has to be greater than A. And C plus A has to be greater than B. If it does not fit that theorem, then it is not a triangle. So now let's finish up with the Pythagorean theorem. You guys should have seen this before, and it just says that if a triangle is a right triangle, then a squared plus b squared equals c squared. So if we look at our triangle, you have A, B, C. We have our right triangle. We have to make sure we keep C as our hypotenuse, which is our longer leg of our right triangle. So you can see if it is a right triangle, then a squared plus b squared equals c squared. So, for example, we can look at a triangle with lengths 3, 4, and 5. So we know this is a right triangle, so we can plug in 3 squared plus 4 squared and see if that equals 5 squared. So we have 9 plus 16 equals 25. 25 equals 25. And there we go. So we have these things called Pythagorean triples, which are just some very commonly used numbers for our sides, where they are nice whole non-zero whole numbers. So that one was 1. So we have 3, 4, 5. We've also got 5, 12, 13. We got 8, 15, 17, and 7, 24, 25. Now these are ratios, so we could also use anything that is a ratio of these numbers. So for example, if we multiplied all of our 3, 4, 5 by 3, 9, 12, and 15, those also work as a Pythagorean triple. So we could do that for all of these because these are all a ratio. So again, these are our Pythagorean triples. Alright, so we'll come in and do a lot more practice and go through these proofs and stuff tomorrow.